Hi, everybody. So today I want to cover electric fields. So in a previous lecture, we talked about Coulomb's law and the force between two charged particles. Now, the fact is that these charged particles aren't touching, right? And so that means that the Coulomb force can act over a distance without any kind of contact. And any kind of force that we say can act over a distance without contact, we call a field force. Now, there's four fundamental forces of nature: the electromagnetic force, gravity, the strong force, and the weak force. Gravity is covered a lot in Physics 1, and we're covering the electromagnetic forces in Physics 2. And strong and weak forces are usually covered in more advanced physics classes. But all of these forces are field forces. In other words, they can act at a distance without physical contact between the objects. So the electric field is no different. They can act through space, no physical contact. Now, Michael Faraday was one of the ones that developed this concept of a field in terms of electric fields. And he believed, and he was correct, that the electric field is a thing in and of itself. And in fact, later, we'll even talk about how electric fields are energy storage mechanisms, but we'll get back to that. So an electric field is said to exist in the region of space around any charged object. Now, if an electric field is being created, then there has to be some kind of source charge. In this picture at the right from some VPython code I wrote, you have this line charge symbolized by the red balls, and it's created an electric field symbolized by the orange arrows in space around it. Now, if you have another object, another charged object, a test charge, that enters this field. Now, we call it a test charge because usually we think of the fact that charges create fields themselves. And so a test charge would have a charge that's small enough to detect the field, to feel the effects of the field without significantly changing the electric field in space. And that means that it has to be a lot smaller in terms of the size of the charge than the source charge. So I hope that's clear. Anyway, when a test charge enters the region of the electric field, there's going to be an electric force that acts on it due to the presence of the field. Now, the existence of the electric field is a property of that source charge. It's a property of the size of the charge. The strength of the field is the size of the charge, but it's also a property of the configuration of any charges that might happen to be in space in that region. The presence of that test charge isn't necessary for the field to exist, but it does serve as a detector, if you will, of the charge. Okay, so how do we define the electric field? The electric field is defined as the electric force on the test charge per unit charge, okay? So the way that we write that mathematically is we say that the electric field vector E is equal to the force that the test charge Q naught would experience. So E is equal to F naught F divided by Q naught, okay? So you just take the force that a charge would experience in that region and divide it by the charge, the test charge that's there, and you have your electric field. Now, the direction of the electric field is that of a force on a positive test charge. Remember that if you have a negative sign in a vector, it flips the direction 180 degrees, okay? So if you look back at this equation, if you had a negative charge, then that would mean that the direction of the electric field would be 180 degrees off the direction of the force, right? And so the direction of the electric field is that of a force on a positive test charge, because the force on a negative test charge would be in the opposite direction or 180 degrees off. Okay, I hope that makes sense. Because we're defining the electric field in terms of the force per unit charge, the SI units of the electric field are the SI units of force divided by the SI units of charge, which is newtons per coulomb. So we can say that the electric field exists at a point if a test charge at that point experiences a force. In other words, in order to find a field, you need some kind of detector, and that detector is going to be a charge. To drive home this point that the electric field points in the direction that a force on a positive charge would point, let's consider the following scenarios. We have the equation F equals QE when you rearrange. Before we defined it as force per Q, but now we're just moving it to the other side of the equation. So this is only valid for point charges, by the way. And so that means that, of course, you're really kind of detecting forces on things like electrons or protons or ions of some kind, small things, right? For larger objects, the field is going to distort over the size of the object, okay? Let's just say that you had a field in space and it was kind of pointing radially outward, which we see a lot. If you had a really big thing next to it, then the direction that it points might be different to the left-hand side versus the right-hand side of the object. So that makes sense. So we're really talking about this equation in terms of small, tiny little point charges. Now, if the point charge is positive, then the force and the field are in the same direction. So that's scenario B there, okay, where you have the shorter pink arrow being the force, and then the larger red arrow being the electric field in space. Scenario A is just the field sitting there being all happy by itself. And then here comes the charge, and F is equal to QE means that F and E are going to point in the same direction and be parallel if Q is positive. But if Q is negative, then the force and the field are in opposite directions because introducing a minus sign flips the direction of a vector 180 degrees. And so here you have an electric field pointing up and to the right, while your force points in the opposite direction down and to the left, okay? All right, so let's use this idea of fields and everything like that in terms of an example problem. So what are the strength and direction of an electric field that will balance the weight of a 1 gram plastic sphere that has been charged to -3 nanocoulombs? Okay, so that's the question. Strength and direction of a field that would balance the weight of a 1 gram sphere charged to -3 nanocoulombs. All right, so to solve this problem, what you would first do is a free body diagram, which I've shown here on the right. Remember that in a free body diagram, you draw the object and you draw all the forces acting on that object. In this case, we're ignoring anything else and just concentrating on the force due to the field and the force of gravity on the object. Now, gravity, of course, is going to point down, right? And that's going to be mg pointing down. I've got the vectors in bold here, although that might be a little bit harder to see. So g, the acceleration due to gravity, is in bold, and e, the electric field, is a vector that's up, and it's going to be in bold as well. Now, I've drawn the mg gravity as a black arrow, and the force that the charge would experience due to the field is QE. In order to cancel it out and have the little plastic sphere just hover there, since mg is down, QE must be up. And also the magnitudes of those two arrows, the size or length of the arrows has to be the same so that the net force on the little plastic sphere would be 0 so that it would hover. Otherwise, if gravity was larger, it would fall down. If QE was larger, it would accelerate upwards, right? That's how that works. So here, the sum of the forces in y, the y direction is the direction I've designated as up, down here, has to be QE minus mg. Now remember, the sign of a vector has to do with the direction it points. I'm calling down negative and up positive, so that means that QE is up and mg is down. QE minus mg has to equal 0, okay? So now if we plug numbers into what we've got, -3 nanocoulombs, a nano is 10 to the -9, so that's -3 times 10 to the -9 coulombs times E, which is our unknown here, minus the mass of the bead times G. The mass of the bead is 1 gram, which is 0.001 kilograms. Remember that the SI unit of mass is the kilogram, not the gram, and you have to convert everything over into SI in order for this to work, okay? So I have minus 0.001 kilograms times the acceleration due to gravity, which is 9.8 meters per second squared. And then that's equal to 0. Now, when I rearrange that equation, I would end up then with QE equals mg, right? So QE minus mg is 0, so I can set QE equal to mg, okay? And then I would divide through both sides by q to solve for E. So I would have E equals mg over q, right? Now, when I plug in those numbers for m, g, and q, then I end up with E is equal to minus 3.27 times 10 to the 6 newtons per coulomb. The minus sign indicates that the electric field points down, okay? So here, the field points downwards because the charge is negative and the force must be up, right? I hope that makes sense. Now, If you remember Coulomb's law, what we said in Coulomb's law was that the magnitude of the force between two charges is equal to the product of the magnitude of the charges divided by the distance between them squared times the fudge factor constant called the Coulomb constant, K, okay? So K is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. That's one of those fundamental constants of nature. So here we have F is equal to K, little q, big Q over R squared. Now I wrote it little q and big Q here because remember that I said that I was going to use a big Q for big charges and a little q for little charges. And the F equals QE thing, that Q is the little q, is the test charge, a little q. Okay, so I'm talking about what the force between a big source charge and a little test charge would be, right? So if I want to figure out what the electric field would be due to the big source charge, right, then I would do E is equal to F over little q, and then that would give me K big Q over R squared. So if you have a source charge, right, establishing an electric field, the magnitude of that field at a distance R from that source charge is going to be K big Q over R squared. So that's the magnitude of our electric field, okay? Now, always remember that fields, electric fields, and forces are vectors, which means that they have a direction, not just a magnitude. So let's talk about what the electric field direction will be, okay? All right, so now we're going to talk in terms of our source charge, which is Q here in this picture. I stole this picture from somewhere else, or I would have made it a big Q. But anyway, Q is the source charge here, and then Q naught is our little test charge. All right. So we have a field Q, which is in the left column a positive charge, and in the right column a negative charge. Positive charges here are shown in orange, and negative charges are shown in blue. Okay. So if the source charge in the leftmost column is positive, a big positive source charge, okay, then a little test charge Q naught would be pushed away. They would be repelled from one another. So that shows that in this upper quadrant here, the blue arrow, which is our force that the Q naught would experience, would be up and to the right at that point, okay, because it would be feeling a force repelling it directly in a line connecting them between Q and Q naught. We talked about that in our Coulomb law lecture. And so if we have a positive charge creating that field, then that must mean, since we're taking a positive test charge Q naught, that the electric field would point away from that positive charge, okay? So that's the left column. The electric field is pointing away from the positive charge. And in fact, it's going to point radially away from a positive test charge. So if you have a positive test charge all around it, okay, the electric field is going to be pointing radially away from the positive source charge all around it. Because no matter where you put your positive charge in space, be that above it, below it, to the right, to the left, to the front, or the back, right? Wherever you put your positive test charge, it would be pushed away, okay? And so you can kind of think of it as a big spiky ball with electric field lines sticking outwards in all directions, like a porcupine or something. Okay, so the electric field is going to point away, radially away from a positive test charge. Now, if you had a negative source charge, which is the right-hand column here with the blue Q source, okay, then if you put a positive test charge in the presence of that negative source charge, it would be attracted to that negative charge because opposites attract here, right? Okay, so that means that the force that Q naught would experience if it's up and to the right from the source charge minus Q, right? It would be pointing down and to the left. It would be attracted to the charge, and so it would go down and to the left, okay? Now, that must mean that since our test charge is still positive, it's a positive charge, right, that we're testing this big negative source charge's electric field with, that the electric field vector at that spot would also point down and to the left because the field points in the direction that a positive test charge would feel the force, okay? And so if the positive test charge is up and to the right of our negative charge, then that means that the source charge, the test charge is going to be attracted to the source charge, and the force and the field would point down and to the left. And so that must mean that for a negative source charge, that the electric field lines point radially inward towards that negative source charge, okay? So electric field lines point away from positive charges and towards negative charges, okay? Now, at any point, remember, superposition is obeyed. So if you have multiple sources, then the electric field at a given point away from those sources is going to be the sum of the fields from all of the sources. Okay, so you have to consider not just one source charge, but all the source charge that might be in the region, okay, and sum up the effect from all of those source charges in order to get the total electric field. And the equation that describes that is E total is going to equal to E1 plus E2 plus E3 and so on and so forth. You just keep adding up. Okay, so let's do an example of superposition here. So let's read through it together. You have a positive 2 nanocoulomb source charge, and it's at the origin. And then you have a negative 4 nanocoulomb source charge, and it's at a position of x equals to 1 centimeter away from the origin. So at what value of x coordinate could you place a proton so that it would experience no net force? And would the net force be 0 for an electron placed at that same position? Okay. Now, sometimes when I see a word problem written out like that, I like to draw myself a nice picture because, you know, pictures are worth 1,000 words, to borrow a cliche. So let's look at that. Here's the little picture that I have chosen. I've got my x-axis here, and I've got it marked off in increments of centimeters, okay? Now, what I've done is I have represented the charge at the origin as a yellow circle and the charge at x equal to 1 centimeter as a red circle. Okay, so those are my charges, all right? Now, remember in the example, it said you have a positive 2 nanocoulomb charge at the origin and a minus 4 nanocoulomb charge at x equal to 1, okay? So the one at the origin is positive, the one at x equal to 1 is minus 4, and it's negative. So the yellow is positive, the red is negative here, okay? Now, I've represented the electric field lines from each one of these with just this simple little sketch. I've got green arrows here because green's a little easier to see than yellow. So I've got green arrows pointing away from the yellow dot here. And then I've got red arrows pointing towards the red dot, okay? The red arrows are for the red negative charge, and the green arrows are for the yellow positive charge, okay? So the positive charge is going to make the electric field point away, which would be to the right for x greater than 0 and to the left for x less than 0, right? That's what the green arrows are telling us. And then for the negative charge, it's going to point towards on both sides. So that's going to be to the left for x greater than 1 and to the right for x less than 1. All right, so that's what's going to happen. Now, let's discuss conceptually what would happen here. We have our equation F equals QE. So the question said, let's read over it again together. At what x coordinate could you place a proton so that it would experience no net force? Now, protons are definitely test charges. The charge of a proton is on the order of 10 to the minus 19 coulombs. That's 10 to the minus 19. And nano is 10 to the minus 9. So the proton is 10 orders of magnitude smaller in charge than the source charges. So it definitely qualifies as a source charge. Okay, so or as a test charge. So at what x coordinate could you place a proton so that it would experience no net force? And would the net force be 0 for an electron at that same position? Okay, so protons and electrons. Okay, now, when the electric field is 0, right, then F equals QE equals 0. So the force will be 0 when the electric field is 0, regardless of whether the charge itself is a proton or electron, regardless of whether the charge is positive or negative. So we just need to find the place on the x-axis where the electric field is 0. And if we find that place, then the force on any charge, regardless of sign, would also be 0. So the answer to part B is yes, the net force would be 0 at this position for both an electron and a proton because the electric field is 0 there, okay? So now let's find the place where the electric field is equal to 0. Before I flip slides and go to the one with the solution, let's talk about this conceptually. Would this place where the electric field be 0 be at x greater than 1, between 0 and 1, or for x less than 0? Where would it be? Okay, well, I can tell you where it's definitely not, and that would be between the charges, between 0 and 1. Like if you look at our little sketch here, the electric field for the positive charge at x equals 0 points to the right between 0 and 1. And the electric field for the negative charge points to the right between 0 and 1. So with both of them pointing to the right, there's no chance of any kind of canceling out. So it's definitely not between 0 and 1. Okay, now let's also talk about the less obvious place where it won't be, and that's for x greater than 1. See, the fact of the matter is that your charge at 1 centimeter is -4 nanocoulombs, and the one at the origin is +2 nanocoulombs, and 4 is larger than 2, right? I mean, it's a bigger charge. So if you're to the right of x greater than 1, you're going to be closer to the red than the yellow, and also the red is bigger than the yellow in terms of its magnitude of charge, right? And so that means that you're definitely going to have a field point left because the red arrow will be longer than the green arrow, right? Due to the fact that the 4 is bigger than 2. Okay, you're closer to a bigger thing. And so that means that the bigger thing will definitely dominate. The only way to get away from the bigger thing is to be further away from it, right? So here you have the green arrows pointing left, the red arrows pointing right. You have a chance of cancellation there because you're going to be closer to the smaller charge and further away from the bigger charge. So it's got to be for x less than 0 that you're going to have cancellation. I hope that makes sense. Okay, so it's going to be x less than 0 is going to be where it is. Now we just have to find exactly where it is, and I'll show you how to do that. Okay, so what you've got to have is the field at that point equaling 0, okay? The net total field. And so what that means, let's go back to our picture. If the net total field equals 0, then that means that the red arrow has to point right just as much as the green arrow has to point left. In other words, they're pointing in opposite direction, but their magnitudes, the size of the field at the point where the field is going to be 0 has to be equal, okay? So using the equation for the electric field for a point charge, remember that the electric field for a point charge, the magnitude of that field is kq over r squared. K is the Coulomb constant, Q is the magnitude of the charge, and r is the distance from the charge, right? So you've got to have kq over r squared for the yellow charge equal to kq over r squared for the red charge in order for that to be true. Okay, so our Q is 2 nanocoulombs, which is 2 times 10 to the minus 9 coulombs, and 4 nanocoulombs, which is 4 times 10 to the minus 9 coulombs, okay? We've taken care of the positive or negative because we're saying that their magnitudes, the magnitude, absolute value has to be equal, okay? So you don't need to put the minus signs in, okay? Now, the distance I'm calling the magical point where the electric field is 0, I'm going to call that distance from the origin D. Now, yet again, it doesn't matter whether it's positive or negative here necessarily because you're going to square it anyway, but we're just calling it a distance, okay? We're calling it a distance. And we're solving for what that distance is. So kq over d squared, which is the distance from the origin, is going to be equal to the other one, k times 4 times 10 to the minus 9 coulombs over d plus 1 squared. Okay, now, why the plus 1? All right, let's pick some magical point. I'm going to put it right here, okay? This is where, let's just say, this is where the magical point where e is equal to 0. All right, now, if I call that distance between the yellow dot and this magical point, if I call that d, okay? Then that means that since there's 1 centimeter in between this origin yellow dot here and D, then the distance between this magical point here and the red dot would be D plus 1. Okay, so that's why I've got D plus 1 there. All right, make sense? Okay, so K times 2 times 10 to the minus 9 coulombs over D squared is equal to K times 4 times 10 to the minus 9 coulombs over D plus 1 centimeter squared. All right, that's where the electric fields from the two charges will balance. All right, now let's talk about things that are going to cancel out. K is on both sides of that equation. K cancels out. I have 2 nanocoulombs over here and 4 nanocoulombs over here. So if I divide both sides by 2 nanocoulombs, then I have on the left 1, right? Because 2 times 10 to the minus 9 divided by 2 times 10 to the minus 9 is 1. And on the right, 4 times 10 to the minus 9 divided by 2 times 10 to the minus 9 is 2. So I have 1 over D squared equals 2 over D plus 1 centimeter quantity squared. Yay me. All right. Now, I can cross multiply here, okay, cross multiplication. So I'm going to take the D squared, I'm going to multiply it on both sides. So I've got then a 2D squared on this side. And then I'm going to cross multiply this D plus 1 quantity squared and put it on the left. Okay, so that's cross multiplication. So I have 2D squared is equal to D plus 1 centimeter quantity squared. Okay, cross multiplying. And so then that gives me 2D squared is equal to, if I expand this square using the FOIL method, then I get D squared plus 2D plus 1, okay? 2D squared plus 2D plus 1. Now I'm going to take the everything over to my left-hand side. So I'm going to do 2D squared minus D squared, that's D squared. And then I'm going to do taking 2D over to the other side, so that becomes minus 2D. And then I'm going to take 1 over to the other side, and that's minus 1. And then that is equal to 0. So D squared minus 2D minus 1 is equal to 0. Okay, now you're going to have to go way back in time to whenever you covered this in your high school or middle school career. Ready? You remember the quadratic equation? You might have learned a little song that went with it. And it was like, if you have ax squared plus bx plus c is equal to 0, then you might remember x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. I don't know if you remember that, but anyway, they taught it to me. So there you go. So this is the quadratic formula. And if you don't remember that, don't worry. Here's a website. Math is Fun is a really nice resource, I think, for a lot of folks. You can copy and paste that website and it'll take you to a page that'll remind you all about your 8th and 9th grade years when you probably learned the quadratic formula. Okay, so there you go. Math is Fun. You can use in a simple quadratic like this, where you have a quadratic equal to 0, you can solve for the roots of that equation. And so using the quadratic formula, then you can see here that D is going to be equal to 2 plus or minus 2 root 2 over 2. And remember that our units here are centimeters. And so that gives us 2.41 centimeters. Okay, so that gives us our X coordinate. Now, this is the distance from the origin. Remember, we said it was to the left. So 2.41 centimeters to the left of the origin is at an X coordinate of minus 2.41 centimeters. X is equal to minus 2.41 centimeters. So that's where we've got it. Okay, so that was a little harder example than last time. Hopefully it exercised some long dead synapses. You've got more examples in your textbook, and I'll link to some more examples below that I didn't do. And I hope it made sense though, and I'll see you around.